Hi, John. Good morning. Yeah, you
Hello,
don't
sir.
open your camera, but thanks anyway. If you're still having troubles with your camera, then or rather your internet, it's perfectly fine to have your camera closed. So just wait for them. So what I want to do for this session is to uh, hasten up a bit, pick up the pace of the discussion because I think I burned so much time explaining the nuances of the statistical methods. I think at this point, we just have to cover the basics and the foundational stuffs. And then eventually, maybe on the third or the latter portion of the course, or rather the section for statistics, that's the time that I can maybe deepen the discussion. So I tend to be carried out sometimes. Um, so yeah, I'll be very structured this time just to cover everything that we need to cover. So yep, just wait for them. Wait for them, and then you can do the session with the other group.
Okay, sir. Thank you.
Hi, Jeff. Welcome to the meeting. Let's just wait for the others before we proceed with today's lecture. Hi, Asiba. Welcome to the meeting. Now that we have a quorum, I think we can start now. So, welcome to, I think, the fourth lecture on statistics. So, as usual, we'll do a quick recapitulation of our discussion the last time. So, let me share my screen. Um, so, let me do a quick recap of our discussion. So, I hope you enjoyed your long weekend, your quick vacation. We have to push on and finish this cohort in a good note. Okay.
Hi everyone.
Hi, Iba.
Sorry. Yeah,
No,
my
no
mic was
worries.
off and I was
Yeah.
talking. Thank you.
Yep. Sure. Sure. So yeah, I hope you are seeing my screen. So the last time, we had a very deep discussion about correlation and linear regression, as well as independent sample t-test. So let me just refresh a bit of what this methods are all about. So for correlation, um, specifically the Pearson correlation, you use that when your level of measurement is at least ordinal. And the Pearson correlation would allow you to identify if significant relationship exists, or significant linear relationship exists between your x and y variables. And aside from that, you can measure, right? You can measure the strength of that relationship. So correlation, as compared to the association that you would do during chi-square test, are different. Okay, they are different. Association is a generic term. Um, it just it just means a generic form of relationship, whereas the correlation is a specific type of linear relationship. Okay? And chi-square test, you use that for categorical variables. And we have this linear regression. So we said that regression means that your target variable is of a numerical level, right? It could be either ratio or interval. So we use linear regression after we have established that there is linear relationship between your x, or at least your pair of x and y. You would see um, the similar results. You would quantify the impact. You would quantify the effect, and the benefit of doing linear regression is that you can do prediction. That's something that you cannot do with just plainly correlation analysis. So in linear regression, the very basic one is the simple linear case in which you have one predictor variable x for your dependent variable y. So the dependent variable could be called target, it could be called dependent, it could be called what are the terms that we use for that, response. Okay, so all of those terminologies pertain to the same thing. Okay, your dependent variable, the one that you want to understand, the one you want to predict through these values of your predictors or x variables. So the example that we had was, for example, the you want to predict the sales of ice cream, and you want to use the temperature as a predictor or x variable. So we haven't discussed the other aspects, like um, how can we incorporate confounders, right? So for example, you want to understand the relationship between um, heart attack and ice cream, because you observe that whenever the sales of ice cream increases, the incidence of heart attack also increases. So if you think about it carefully, there's no causal relationship between the two, right? But there is correlation. But the reason for that would be because of another type of variable called the confounding variable. The confounding variable in that specific example could be temperature. The reason why you observe that there is high correlation between the incidence of heart attacks and also the sales of ice cream is because of the third variable, temperature. right? The higher the temperature, the higher the incidence of heart attack. So we will be talking about those things, those aspects on the last week of the statistics portion because um, real variables, real data sets tend to be very complex, and you cannot just model the behavior of one variable directly or uniformly. You have to consider other aspects such as confounders, such as interactions, and so on. And we also discussed this method called t-test. So t-test has different forms. It could be one sample. One sample is you have a hypothesized population mean that you want to verify through a sample. So you check the differences. If if the corresponding p-value from the statistic is very low, less than zero point zero 0.05, then you have an evidence to say that it is indeed different from the hypothesized value. It could be also an independent case in which you have two groups and you want to say that one group is better than the other or inferior than the other, then you can use independent sample t-test that will utilize the pooled variances between or from the two groups. So that's basically the principle that's being used in A/B testing, which is a very common method in data science and analytics because most of the time you want to base your decision uh, in data in empirical evidence. So in order to do that you need to do experiments and analyze your data coming from that, and that's where you will be applying independent sample t-test. Okay, so aside from that, there's another flavor of rather t-test called paired or dependent t-test. So this is across time. So you have the same set of samples, the same set of experimental units, and you will be measuring their initial characteristics before you introduce a treatment, and after some time, maybe um, during the duration of the experiment, um, you would hypothesize that it would increase or decrease that characteristic. So after the end of the experimental duration, you would compare, okay, the ending measure versus the initial. So that way you can say that okay, the experiment increased, or the not the experiment but the treatment increased or decreased the characteristic, whether it could be weight, it could be the number of visitors in your website. Maybe you try to incorporate like a chatbot, for example, and observe if it would drive more visitors in your website, or you tried combining different colors, you tried incorporating new things, and you want to have an unbiased way of measuring its performance. So you can do that through a dependent t-test. And yeah, so basically in different industries and different fields, they're calling this method of in different ways, like um, A/B testing, but basically those different names, they are referring to the same method. That's just being applied to this respective fields and disciplines. Now, we also talked about geometric mean and coefficient of variation. The classic example for the coefficient of variation is your you want to compare the variances of two things that are significantly different in terms of magnitude, like comparing the variation of the prices of toilet papers versus car prices. If you just apply standard deviation, it will always appear that in terms of magnitude, the prices of the car would fluctuate significantly larger, just because of the nature that car prices are more expensive than toilet papers. So in order for you to have or to eliminate that that problem regarding the difference in the magnitude, you can use coefficient of variation, which is just you just divide the standard deviation over its respective means. So in that way, you are basing the variation on their own means instead, and the unit would be in terms of percentage. So it will not be based on the unit that you used for the individual measures. So the higher the coefficient of variation, the more you approach the 100%, then it means that it is more varied. And geometric means, so as compared to the typical arithmetic mean, this is more applicable to, for example, you have an exponential growth, or you are considering or analyzing a data that is across time, so or in rates, I should say. So that's the time that instead of the arithmetic mean, you would be using geometric means. Okay, and we had this practice, I think, that you did with John in the lab. So why is it very important? Why am I stressing out the importance of being able to identify the data types before you proceed to any type of analysis, whether it is basic analysis or advanced? So simple as um, generating the summary statistics. So there are times that you would encode a variable in terms of numerics, say one and zeros, one for yes and zero for no. And you can generate summary statistics, but it doesn't necessarily mean that it's already valid. To give you an example here, this is an actual data set that I'm um, currently analyzing, and I want you to see this point that I want to stress out. It doesn't mean that you can compute for something for a summary statistics. That it then you will compute. You have to make sure that that computation is valid for the variable, or it makes sense to do that. Like for example, this one. So this variable is about diabetes mellitus. So one is for yes if the patient has diabetes mellitus, and zero if not. Of course, if you apply summary statistics with this, you can definitely get an average, for example, and a mean and a max. But it doesn't make any sense, right, to have an average of 0.4. It doesn't characterize this variable that I have just for a while. Okay, sorry about the interruption. My AC, I think, is dying. It's just freezing. Probably there's a leak or something. So going back here, so while this is encoded this way, okay, this is called dummy encoding, and there's a specific purpose for this, especially in the modeling context. We will be discussing that as we proceed along. But the thing that I want to highlight here is that if you set up your data set such as this, you can compute for the summary statistics. But again, ask yourself, is it valid to do so? It doesn't mean that if you can compute something, you will immediately compute it. Make sure that you ask yourself, okay, what is the level of measurement of this? It is currently on a nominal level. And for a nominal level, what is valid to be computed, what statistics to be computed would be just the count, the frequencies, and the percentages, right? Because it doesn't make any sense to have like an average of 0.5 here. We don't have any category associated with 0.5. We only have one for yes, zero for no, right? So in those cases, in most cases, that's the first thing that you need to do. Ask yourself, what is the level of measurement of this variable? And based from that, you will know what you can validly do on that variable. Like for example, this one, it's a BMI, right? So this BMI is a numeric variable that is computed by um considering the weight and the height. So it's just like the height divided by the square, um, or the weight divided by the square of the height in terms of meters. So, well, this is on a ratio level, so you can do so many things with it. It has the highest statistical power. And some other things here, like for example, this BP, blood pressure. So it is basically composed of two things, the systolic and the diastolic, right? So if you want to use this as a numeric, you cannot just immediately plug in this in your model and um, and try to compute for a summary statistic, but it won't allow you to do that because you have the slash in there. So what I did with this is I separated the systolic blood pressure and the diastolic blood pressure so that I can compute for another measure, a composite measure for this, like a mean arterial pressure, or I can standardize both and incorporate them separately in my model. So those kinds of things, those kinds of strategies that you need to employ in your data. But again, the first thing to ask yourself is what level of measurement is this variable on? And based on that, okay, after that, can I convert it into something that into a level of measurement in which it would fit my intended analysis? So that's the typical route that you should follow. Now going back here, I'll be closing this one. So I have here a map, right? A map of statistical analysis, typical statistical analysis that you would typically do. So for example, here you want to test the significant differences. Um, so if you have two groups, then if they are independent and the data is ordinal, you can either use the Mann-Whitney test. We will talk about this. This is called a non-parametric test, a non-parametric counterpart of the independent sample t-test. Why non-parametric? It's because it doesn't rely on a specific distribution as compared to independent sample t-test. And the independent sample t-test assumes that both of the groups are coming from the same population, typically from that of a normal. Now, um, as you can see, the form of the data here is being asked because, again, the type of analysis that you would do with that is based on the form of data that you have, the level of measurement. Now, if you're comparing multiple groups, not only A, B, you might be comparing A, B, C, D, or even more, then you have analysis of variance. So why is it that you have to have ANOVA, or analysis of variance, instead of just using independent sample t-test? It's all about um, the error. So remember that the alpha value that we talked about earlier refers to your allowable error, usually set around 5%, right? So if you if you consider more than two groups in an independent sample t-test, the error, okay, will be multiplied by 3 if you're considering three groups. That will be around 15%. And I don't think that you would be risking that much, okay? If there's an alternative that would allow you to hold that error in just 5%, similar with the two group case. So we will be talking about the nuances, about the details of analysis of variance as we proceed along. But that's the main reason of having analysis of variance. It is an extension of independent sample t-test for more than two groups. Now, as you can see in here, you see the chi-square analysis that we talked about in here. It could be about a theoretical distribution. This is something that um, we haven't discussed about because we haven't yet discussed probability distributions. So basically, um, there's a way for you to test whether your data follows a specific distribution, and that is you can do that through a chi-square goodness of it. Okay. And this is the one that we did. We use chi-square analysis to test for association of what? Of categorical variables. And of course, as you can see, there's a separate section here for summary statistics, because summary statistics, while they are very basic, they are very easy to generate, they are extremely helpful. Okay, the summary statistics will give you an idea if whether there's something wrong with your data set. If there are presence of outliers, you can detect them by simply going to the summary statistics. And as you can see in here, you see the regression, right? So if you want to explore the relationship even deeper, and this is the one that we did last meeting, the Pearson correlation coefficient. And there's this counterpart. Um, you might wonder, Jeff, you told us that even if ordinal, you can still use Pearson correlation. Yes, but in some cases, if it fails assumptions, like for example, um, if your data set is significantly different that of a normal, then you have to use the non-parametric counterpart, which is the Spearman's law. So by now, maybe it's still not complete. Um, Maybe listening to me while going over this different methods sound how should I say this, overwhelming. But as you proceed along, as you continue with your journey in analytics and in data science, you would find these methods. Um, you would identify right off the bat in which method you'll be applying to your data set, depending on what you want to accomplish. So it's all about experience. It's all about having that experience, hands-on experience of first identifying the um, type of data, next type of analysis, and so on. So it's perfectly fine if you feel that it's overwhelming at this point. But I guarantee you that as we proceed along, slowly everything would make sense. Okay. Now I'll be proceeding to my second lecture. Well, supposedly second, but um, I think I have overestimated, uh, or I should say underestimated the time that I need to invest for one topic for one lecture. So let's proceed to the second one. I have to close this now and switch to the next. By the way, do you have any questions, guys? Do you have any clarifications on the things that I just went through? Okay. Let me share my screen again. Again, you can interrupt me anytime if I'm speaking too fast or if I say something confusing or doesn't make sense. Just let me know. Okay. So for this second lecture, our focus would be on data collection and also sampling techniques. So going back to the example, to the idea of taking blood samples to identify what's wrong with your body, we also do the same principle in statistics. It's not necessary for us to get all the parts of the population in order to arrive into a conclusion. Similar to your blood sample, you don't need to drain all of your blood to identify what's wrong with your body, to identify what specific sickness you have. Okay. Oftentimes, you would hear from people that they are skeptic about statistics because how can they argue that how can the statisticians arrive into conclusions through just a simple subset of the millions of population in a country, like for example predicting who will win an election or estimating a particular economic variable. So um, it's common for people to say that because they don't have any idea about probability distributions, right? Of course, these estimates they are not really 100% fail proof. They're not 100% accurate, but at least we have this measurable level of confidence. We have a measurable level of precision and accuracy. So based on those, we can have um, we can have database recommendations, and we can with some degree of confidence say that this is what's happening in the entirety of the population. So in order for us to do that, in order for us to have a um, trustworthy estimate, right? Trustworthy meaning it's precise and accurate. We have to know the different processes and the different methods of collecting data. Can you think of any ways? Can you identify different forms of data collection? Any one of you guys? Do you have any ideas? Grace, please.
Survey?
Grace,
Survey?
your volume is significantly low. I'm not sure if it's just on me, but okay, perfect. Surveys. So surveys typically on the form of questionnaires, right? So it's a complex task. Okay, there are statisticians that focus their career on doing surveys. So in surveys, usually you get the opinions, you get the um, mostly opinions, opinion based surveys. Others, well, sometimes you can also do like an objective type of survey, but it's quite difficult. But yeah, we have surveys and interviews, right? Now, I want you to identify what are the benefits of doing surveys and also the disadvantages of doing it over interview. Okay, let me provide one. For topics that are very sensitive, it's quite difficult to get honest answers through interviews, right? For example, um, it could be as sensitive as topics about religion, about sexuality, about very very sensitive topics in society. Okay, because there's an interaction between the interviewer and the interviewee, and oftentimes if the interviewer is very dominant, if they can control themselves, they have the ability to impose their belief on the interviewee. Okay, there are oftentimes cases such that. Okay, and Grace says here the randomized sample isn't representative of the population, i.e., college students. Okay, we'll be
I
talking
think
about that. Yep, Jeff.
also I think it's the uniformity.
Okay,
The
uniformity.
uniformity of the type of answers. I guess like you'll all have the same type of questions, right? And then
Mhm.
those data that you can plug into your regression analysis. Because interview you maybe I don't know, maybe if you ask the same question then fools you because but then survey usually you're everybody have the same type of answers and then so your you deal with the same type of data set from
Yeah,
everybody.
yeah. So it's more structured. Your data would be more structured in a questionnaire, right? Which fits perfectly for a quantitative study because you have structured it in a way that you will be able to plug it in your analysis, right? However, there's also benefit in doing interviews, particularly if you're doing qualitative research, because the quality, the substance of answers that you will get from doing interviews is much deeper. It's not constrained as compared to a questionnaire. So that's one benefit when you are doing a qualitative research. You can get more information because there will be uh, a follow-up. There is a possibility of doing follow-up questions when you're doing interviews. So the depth of information that you will get via the interview would be deeper in a sense as compared to that of a survey. However, it's less structured as compared to a questionnaire, right? On a questionnaire, it's restricted because oftentimes those are just close-ended questions. Yes, you might argue that you can include open-ended questions in a questionnaire or in a survey form. However, most of the time, people would just say short phrases. They would answer short phrases in those open-ended spaces, open-ended questions, as compared to doing interviews. Also, in interviews, you can observe their bodily language, right? You would observe um their eye movements because most of the time you would be able to measure, you would be able to by intuition alone, you would be able to somehow get an idea if a person is telling a lie or not, right? So by experience you can develop that ability to see through people if they are telling the truth. Okay, but again, the bias would be much higher in an interview because if the interviewer is not that experienced, then there could be a clash of the of beliefs, the belief of the interviewer and the belief of interviewee, and we don't want the interview to result to a debate. But sometimes if you look into interviews done in TVs, instead of interviews, it's becoming more of a debate because there is a clash. There's a clash of beliefs. So those are some of the things that um, you need to consider between doing surveys and doing interviews. Okay, but for our discussion, aside from focusing on those concepts, we will be looking into the technicalities behind. I'll be using here Python to show to you the mechanism under the different types of data collection methods. Okay, like for example, if we want to do a probability sampling technique in getting those samples, what happens when you do a simple random sampling? So I'll be using Python to show you what's going on with it. Okay, what's the actual process that's happening when you do simple random sampling. Eventually, to to get to this point that Grace has been saying, representativeness. That's our main goal. Okay, in data collection, particularly if you're planning to do inferential methods, you have to achieve representativeness, right? Because how can you generalize if the method of your selection is based on your whims alone? Like for example, you feel comfortable to just survey your neighborhood, but you're generalizing the result for the entirety of the state. That doesn't sound right, right? If you want to generalize, then there should be a representative from each of the location, each of the city in that state, so that you have a you have a more varied and representative answer. So those considerations, while while straightforward, it's quite difficult to do that in actual because of several constraints, right? Especially if your location is containing a very large number of with a very large population, or if there are um, existing existing um, how do I call that, resistance. Like typically in a location, there are groups, right? Um, there are natural groupings that exist in that location, and there are there are typical um, the problems that these people are experiences with each other. So while it's simple to talk about that theoretically, in actual practice, it's quite expensive and time consuming to have a representative sample. So we want to be as methodological as possible to make it a reality. Now, data collection. Let me just define it here. Data collection is a critical step in any statistical analysis. The accuracy and reliability of conclusions drawn from the analysis depend heavily on the quality of the data collected. So, as a trained analyst, you don't just focus on the complexity and the level of analysis. You also pay attention to the quality of the data. Once, okay, regardless of how complex and how sophisticated the method is, once you identify something wrong done in the data collection, then the result is already questionable. Okay, once they are not transparent with how the data has been collected, then you should be skeptical about the result, especially with clinical trials, with lab testing and so on. Like one issue that happened here in the Philippines, and this is with an international company. If you're maybe it's been in the news in the US. So there's this supplement company that was on fire because the protein content of their supplement was revealed to be around 8 grams per serving as compared to what they are claiming that's supposedly around 25 grams. And to prove that they're really the what they're marketing is really true, that the product contains 25 grams of protein, they did lab testing. However, there was a question about how the samples were selected. This is easy to fool people if you just want to show them that, okay, we have these lab results and they show 25 grams of protein. You can easily pick, right? During your production, you would enhance you would make sure that the content would be at least 25 grams. So that's the importance of being transparent in how in how your data is being collected, because there would be questions if you will not be transparent. There will be questions about the result, whether you're telling the truth or not, because analysis can be easily swayed, can be easily crooked. Okay, but the data collection, if you um, become transparent with it, it will reveal the truth, whether you intentionally skew the result because of that, or you just uh, committed a grave mistake, and something like that. So that's how important the knowledge of how the data is being collected is. Okay, very important. It the results are anchored, the validity of it, the accuracy of it, um, all of that are anchored on how the data has been collected. And we have here two types of data: primary and secondary. So primary data collected firsthand, right? So just remember that primary, first-hand observation, first-hand information, and secondary, you just collected it from other sources. So is one better than the other? It depends. It depends on your um. It depends on what your goal is. If you're trying to prove that a particular treatment is better than the other, then a primary data would be um, would be better, because everything would be clear to you. Everything would be set up by you. Okay, as compared to secondary data, there would be gray areas on how the data has been collected, how the data has been recorded, and so on. For secondary data, most often these are voluminous types of data, mostly like economic data, um, mostly from companies that really that really do this kind of work. There are companies that are just collecting this they're just repositories of data, and people can buy and organizations can buy this different data sets from them. And we now have data collection techniques. We've gone through some of this, like surveys, experiments, observational studies, and administrative records. So observational studies, I think the best example for this would be psychological studies, right? Um, there will be an observer that records the things that are happening, maybe the movement of the people, the reaction, and so on. But there would be no manipulation. They would just proceed with their natural course of action, and you're just there as an observer, recording the important things that are relevant to your analysis. Most in cultural studies, psychological studies, and so on. But in psychological studies, oftentimes there are treatments also. So they are typically doing experiments and uh, aside from observational studies. We have administrative records. I think this is the typical, right? Uh, we look for sources of data online, or maybe request for them from these different agencies. And however, however, most of the time, administrative records are extremely dirty, extremely dirty. You would expect that the data set will not be on a framework or on a format that you can easily analyze, because these people, they are just there to just have a record of something, and they don't care if that format can be readily analyzed. Their goal is just to keep information. So it's a pain for us. It's a pain for us, well, especially government records. I experienced so many dirty data, so many times I've worked with government data, and they are just horrendous. Okay. Um, I'm not hating on government agencies. It's just a fact that most of them, they don't care about the structure of the data set. It's good if they standardize the procedure, but I think it's an additional work for them, especially if that organization tend to change people in the role. So you would observe that the data set is just really on a unstructured format. So sources of data, we have census. Oh, by the way, um, we have sampling and we have census. Census means that you'll be getting all of the units of the population. That's what census is all about. And sampling is just you'll get a subset of it. Okay, census is expensive, um, both in terms of time and other resources, money, and oftentimes just as conclusive as sampling. Okay, because with census data, and this is what's actually happening. There are tons of errors in encoding. There are tons of problems, especially with the enumerators being lazy. So it's not a proof that if you have a census data, it's already 100% representation of what's really happening, okay, you should leave yourself for some degree of error. There's also a margin of error, even if you do census data. It's not 100% accurate. I guarantee you that. Then we have administrative records. Well, administrative record census could be under it, and databases. So there are tons of online repositories such as Kaggle, Noema, and some other repositories that you can use. You can go to the World Bank website and they have their own database there. If you're into macroeconomic data, then you will have it there. And yeah, since it came from this organization, then you can assume accuracy. Okay. Now, sampling and techniques. Okay. So what is sampling? We've already defined it in a very simple way. But let me go through the formal definition. It is the process of obtaining representatives from a collection of objects or people. So sampling can be done with objects, such as, for example, in a production line, you want to identify, okay, in a production of 1 million, what percentage would be defective. It's being done in quality controls. Okay, in manufacturing, it's being done. You will find statisticians in there as heads of quality control. There are specific methods in statistics that are specifically for that. Okay, so the sampling technique depends on the type of analysis that will be used in the research. Sampling should be done meticulously. That's what I want to stress here, meticulously, to ensure that the chosen are good representatives of the totality. Okay, because again, if you want to infer and generalize the results from your samples, from your statistics, as a good estimate of the population parameter, okay, as a good estimate of how the population looks like, then it must be meticulously selected. You cannot do that haphazardly. If you try to do that, even yourself, you would be asking, okay, whether the result is actually realistic. That's oftentimes why there are results. Even if you go back to analysis, everything looks good. You would observe that there would be unrealistic results just because of how the data has been collected. If they just do it haphazardly without any caution, then there would be repercussions. And here we have, well, the sampling is actually divided into two. Okay, probability and non-probability sampling. So we will not be talking about non-probability sampling here. There's no non-probability sampling that are typically biased, but people do non-probability sampling because it's convenient to do. But I never ever recommend you to do that because it defeats the purpose. Why even go that far studying all this complex methods if at the end you don't have any confidence about your result because you've been lax with your data collection. So we'll focus on our discussion about probability sampling. And what do we mean by probability sampling? It gives members of the population non-zero chance, not necessarily equal. Okay, not necessarily equal. So there's a specific probability sampling technique that is giving all the members of the population equal chances, and that is letter A, simple random sampling. The easiest way to visualize this is this: the fishbowl technique, lottery, in which only one ticket would be assigned to a person. So if I'll be choosing a person here and I want to give you equal chances of being selected, I'll be taking your names, write that down in a paper, put that in a box, and then select one, assuming that the size of the paper are of uniform are uniform, and there would be no way for me to somehow distinguish one from the other. So that is giving you equal chances of being selected. That's the most that's the most idealistic way of getting your samples, giving them equal probabilities, equal chances. But oftentimes it's not the case, right? Like in lottery, you can buy more than one ticket, and your probability of winning would be increased. Not significantly, but you have more as compared to a person that only bought one ticket. Okay, am I still making sense, guys, about the different concepts here? Can I get a thumbs up if you're still following? No, you're not following. Just a thumbs up will do, just to gauge if I'm still doing a good job of explaining these things. So I see Hasiba. I know that Grace and Jeff. Jeff is still driving from work, and Grace is still at work. So yeah, for probability sampling, we have four: simple random sampling, stratified random sampling, cluster sampling, and systematic sampling. From the name itself, you can distinguish each other. Simple random sampling is the one that I told you, giving equal chances to each member of the population. Stratified random sampling, from the word strata, stratum, layers. So you are assuming that you'll be doing collecting in different layers of the population, defining that that layer is important when you decide to do stratified random sampling. And we have cluster sampling. Clusters, there are groupings. So the cluster is different from stratified random sampling in a sense that you typically do cluster sampling when your population is subdivided over a wide geographical area. Okay, so that's when you do cluster sampling. And we have systematic sampling. Systematic is there's a pattern, like every third element, every third unit of the population would be selected. So there's a system, there's a defined rhythm in how you get the population, the samples from your population. So let's have a closer look on this different probability sampling. Again, why are we focusing on probability sampling? Because from this, you can get representative samples. The non-probability sampling technique won't give you that because each of those are biased. Just to give you some examples of non-probability sampling would be convenience sampling. From the word itself, those member of the population that are the most convenient for you to get. So you're injecting so much bias on it. Second would be quota sampling. Quota sampling is just well, assigning a specific number, and after that, you'll just have to reach that number, and then regardless of how you get that number, you will use it as a um, you will use that in your analysis. There is this um, incidental sampling. So those types of sampling techniques, those are not to be used in inferential methods. In a setup in which your intention was to generalize the result for the entirety of the population. Okay. So yep, going back here, simple random sampling. Let's put a spotlight on it. So what do we mean by that? It is the simplest form of probability sampling. Remember, we are assigning equal chances of being selected. When using SRS, the population is assumed to be well mixed. What if not? Then don't use SRS. If it's not well mixed, then you either use stratification because in those strata, in those each of those stratum would have homogeneous characteristic. Okay, but if it's well mixed, meaning there's no um, there's no natural grouping in that population, then the best is to do simple random sampling. Okay. The researcher does not need to consider every member of the population to obtain the characteristic of the entirety. It is the same reason why medical technicians don't drain all our blood. So I just repeated this thing that I've already said earlier. So one limitation of simple random sampling is that it requires you to have a list. It requires you to have a list of every unit of the population so that you can well, in most of the time, um your judgment, your expertise would tell you if the if the units are actually well mixed. And but the problem with that is if you would be doing the lottery method, the simple random sampling, you have to have a list of the units of the population. Okay, so that's one challenge. Most of the time, you don't have that, especially if the population is large. Now, to see what's going on with simple random sampling, I have here. Okay, here's the thing. I just did this in order to show you what's going on. But there's no way that you will do do this simple random sampling in Python. Okay, I just did this so that you will visualize it further. You will understand it further. Okay, but again, you will not do this in Python. This is typically done and planned um, before before even doing the research or before even doing um, the collection. It's a planned thing. Okay, and you don't need any programming for this. So basically here, in order to show you a visualization to make your understanding about the concept deeper, I'll be using pandas and numpy. So here, I just imported them. Okay, well, I think we can. I think this is the most that we can zoom in. So here I just created a sample data set. This is a dictionary, right, guys? You see the structure of curly braces, then you have the keys, and you have the values. We know the range, right? 1 to 100. 101 is not included. It's the stop. And then I just applied here random.randint to get random values. So this is similar to rand between in Excel, but this is how you do that in NumPy. So I've stated here 100, and then starting from 18 up to the maximum of value of 70. So it's just a random process of selecting values in between the two numbers that I have here as parameters, or rather arguments because they are specified. And I have also height and weight. And this line is just a way for me to convert this library, no, this dictionary rather, into a data frame. Okay. And here's just a head to verify if uh, everything's correct. And then this random seed, then this is a random process. If you want to reproduce it, if you want to observe the similar result, you have to set a seed. So this 42 is just an arbitrary number. It could be 3, it could be 4. So that random seed would hold the result the same for every run. Okay, for every run. So basically, after that, we will be applying here simple random sample, simple random sampling rather. And in pandas, you have a sample attribute to data frames. So here we define the sample size equal to 10, which is not a requirement actually. It's an argument in the sample attribute. So you can just replace this with 10, and there's nothing wrong with it. It would still run. And this is just a way to display the sample data set. Okay, the slash n right there is just a way for you to have the next output on the next line. Okay, so random sample. After that, the slash n, what it does is for the next value, it will be on the next line. That's what the slash or backslash n does. So let's see. I'll be opening my Colab and show you um and show you the results. Okay. Again, a caveat: you won't be doing this in Python. just a way for us to visualize the process, the underlying process in a simple random sampling. And I hope I did not delete that. Where is it? Um, Looking for that thing. Okay, where is it? Ah, there we go. This one. ID height. Okay. This is certified. Okay, there we go. This one. Okay. I hope you can see my screen. This collab screen right here. So this is just basically the the one that you saw earlier. Let's try running this. So this is the head of the original dataset, the first 5 rows, and this is the random sample of size 10. Those are randomly selected. We can increase it further. We can specify that we want, say, 30 units, right? And let's display more rows here. Maybe 10 rows would be good. So as you can see, we have increased the number of samples that we have. And this sample method or attribute in pandas is how you do simple random sampling. Okay. So the only time that you'll be doing this in Python is if you're given a data set and it's specifically asking you to do simple random sampling with it. But I think that there would be few instances that you will actually do that. Okay. So probably in interviews they would be giving you a toy data set and you have to um, do random sampling with it. Just take note that you have a sample method or attribute in pandas that readily that can readily be applied um, in pandas data frames. Okay, so it's not actually difficult. The reason why this is a bit long is because of the process of developing the data set. But this part is something that you already know by now. I mean, we're exploring the numpy here, but this random run int is just basically ran between in Excel. There's no magic in it. There's no I should say there's nothing complex here. Okay, there's nothing complex with the rand int. So that's how you do. That's what happens with simple random sampling. It assigns in this DF that you have, it assigns equal probabilities, and then it's just select randomly what would form your sample of size n. Okay, and then after that you would argue that this is a representative of um that data set. So let me show you this. So that random sample that we have is this data frame, right? So let me show you this random sample dot uh say we hit it with the summary, right? Um oh wait. Random sample. Oh. What I want to do is to hit it with a summary. Uh I might be confusing myself. Summary. How do I apply summary? Summary. Okay, I'm summary is not defined. It's not a function, of course, Jack. What are you thinking? Uh, Random sample is a dia So I can do slicing. Let's slice it first. Let's start with age, then hit it with the summary. Oh, sorry. Uh, okay, I'm blocking out. Wait. Uh, summary. What's happening? Get summary statistics. I need the help of. For some reason, this basic things. Again, just like I told you, I have a very short-term memory. Dot describe. Okay, okay. Describe is the way to get the summary. Why do I use um why do I even use the summary function? Could be in R, I think. Okay, anyway. So this is the summary statistics from the random sample that we got. And let's see if it's near to the summary statistic of the actual or from the actual. Okay. So let's do a snippet of this to have a better vision. Um, okay, and then paint. So I just want you to show you something that if it's indeed a representative of the earlier, then we should expect that summary statistics are almost near. Well, um, subject to the existence of extreme values, right? So the means for we don't generate means for the ID. ID is currently a number, but it's a nominal variable, so we don't care about the summary statistics of that. It is supposedly an object, right? It is supposed to be an object. So we start with age. So the mean age from the random sample is 30. The mean age um from the entirety of the dataset is 44. So there's a bit of difference there. Or am I? No. 46. So there's a minute difference, right? There's a minute difference between the mean age in the complete data set and here in the random sample. Standard deviation is almost the same. Minimum should be almost the same also, 50 and so on. So what I'm trying to highlight here, to put emphasis here is if you've taken random samples, um, you have more confidence in saying that the summaries would be almost near to the summaries of the entirety. That's how good doing random sample is. Okay, but again, there are limitations. It's quite difficult to do simple random sampling. You can only do that if you have a complete list. Okay. Any questions about this? Am I making any sense here? Questions, guys. Questions. Again, the point of sampling is to create a miniature, okay, to mimic the population, to have a smaller version of it, because it's easy to navigate. It's easier to analyze. Smaller data set, right? It's less. It requires less resources, right? So yeah, those are the reasons. All clear? You're suspiciously quiet. I'm not sure if I'm doing a good job of explaining these things, or maybe there are parts in here that doesn't make sense to you. Of course, if your data set contains extreme or outliers, um, there would be huge differences, particularly in the range, right? Even with the means, because we're looking into average, right? But that's when you go to the median, right? Because the median, well, it just ignores the magnitude. Okay, guys, any questions? Questions? So can we say that this is a representative? The answer is yes. This is a representative of the complete case. So we can do analysis with this. We can hypothesize that the mean should be the mean of the complete case should be near 46, and we can see that it is 44.47. Not much of a difference, right? So that's how we do it. That's how we do statistics. Get a smaller version of the population, analyze it, um, generalize it for the population. Of course, it will not be 100% accurate, but we are guided that it is near, should be near, assuming that other considerations are also met. Okay. So moving forward with this, um, so that is simple random sampling. Okay. Now we have certified random sampling. We said earlier that with simple random sampling, it is best to use that if you have a list and if the population is equally mixed. But what if the population is divided into groups? Okay, but by whatever, for example, in a class, you would observe that there is natural grouping in terms of characteristics between male and female, right? In a school, there's natural grouping in terms of colleges, right? In a university, those that are taking IT must love computers and technology, and those taking the arts must love arts, right? And others related to that. Those are in the sciences must love the sciences, right? So there's this natural grouping that we can call strata, okay, in the population. And while we can argue that yes, we can still do simple random sampling, if we want to minimize the variances, okay, we can do that by grouping them first, and then in the groups you apply the simple random sampling. Okay, that's basically the idea of certified random sampling. Identify first, define first the groupings, and then inside you do the simple random sampling. Okay, so let me go through the formal definition of this method. So divide the population into strata or layers. Okay, strata from the Greek word stratum. When you cut a rock, there are layers in it inside it. So that's where they got the term. So members of each strata are assumed to have similar characteristics. That's similar to the colleges in a university. Simple random sampling then will be performed in each strata. So you'll be giving equal chances inside the groupings. So you are somehow minimizing the variances as compared to just applying the simple random sampling without considering the groupings. Because with that you're not actually um you're not you don't have the assumption of having equally mixed. Okay. Now let's look at the implementation of that in Python. So basically we'll also use NumPy here. So here in order to define a grouping, I just use male and female. Okay, so those are the stratifications or the strata. The first stratum would be male, the second stratum would be female. And yeah, basically we would be identifying, okay, how many would go to the male and how many would go to the female. So the typical way of doing that is to consider their individual sizes. Say in a population of 100, okay, 70% are females and 30% are males. So 70-30, right? So if you would be if you want to achieve representativeness, then the larger the strata, okay, the larger the strata, the larger the number of representatives. That's called proportional allocation in stratified sampling. Okay, the larger the strata, the larger the number of representatives coming from it. So if you identified, okay, from the 100, okay, where 70 are females and 30 are males, I will get 80, for example. So in order for you to do proportional allocation, you will get 70% of that 80. This is around 56. 56 would be your female representative, and the other 30%, that's around 24, would be your males. So that's how you do proportional allocation. Simply getting more from strata that are large and getting less from those that are smaller. Makes sense, right? That's intuitive. Intuitive. The larger the group, the more varied the characteristics are. So, yep, basically here, this is just the creation of the data frame. npr.random choice is what you would implement if you're trying to um get how should I say this? Random int or rand int is 4 numbers. Choice is 4 categories. Options, categorical options. So you have here random choice, male, female, size 100. So the default probability here is you have 50% male and 50% female. Okay. Now, um, pd.dataframe. This is just a conversion to a pandas data frame from a library, or why do I keep saying library? From a dictionary. Okay. And then this is just printing, then head. Then here, we are looking into the unique values for gender. Of course, we know male and female here. And the sample size that we're taking from the stratified random sampling is 20, right? From a population of 100. So how do we compute the strata sample size? This is basically what I said earlier, right? So you are just getting the number, the counts for each of the stratum. If the stratum is like 60, you will multiply that 60, that proportion to the sample size that you want to obtain. So if you have 100, 60% or 60 are male. So I don't want to confuse you. Let me run this and so that you have a better visual. Let me switch back to Colab because I believe that showing you by parts here would be more intuitive. Let's separate this as this. Okay, these are just processes involved in the creation of the data frame. There's nothing new with that aside from this. Okay, and then this DF head. Let's see the original DF that we have. Then if we hit it with the value counts, you can see the distribution, right? The frequency distribution. So we see that there are more females than males. So basically, what we're expecting is that if we apply proportional allocation, there would be more there would be more females, to put it simply, because they comprise in the total case, the complete case, in the population, they comprise more than male. So there should be more representative, right? So 55% of the sample size. So if you need to have a sample size of 20, then 55% of that will comprise females. That's basically uh, what's happening in here, right? That's what's happening here in this part. So basically here, I just looked into the value counts to see the proportion because I know that this is this 100, right? And then multiply it by the sample size to see the individual sizes. So if we run that strata sample size, you would see the actual thing. So that is 11 for female and 9 for male. Okay, so that is proportional allocation. Allocating more from a strata that is larger um, and less from the smaller. Okay,
Hey Jeff,
questions, guys?
is this what is used for like national polling for
Yes,
politics? Is it stratified because
yes.
of location?
They can stratify it. This is what we did in the last strategy consultancy that I did in the U.S. Um, that was last year. Ah, was it last year? No, no, it was this year. Um, we defined different stratum uh de- depending on the age, because we identify that there's age has something to do with their choice. No, no, no. Let me refine my sentence. We have identified the age brackets in which there is a significant difference in the preferences, voting preferences, like millennials, Gen Zs that are eligible to vote, baby boomers, seniors, and so on. So we identify those um, strata, and then we did the sampling through that, and we observe their preferences. Like for example, the millennials are more into Republicans, so something like that. So we're observing their voting preferences, even their. This is a bit intrusive, but uh, we scrape their social media posting. So be careful with what you post because it's easy to scrape them. If you have an API, like for example, API for the one that we used was from Twitter. So we scrape um, the tweets. Okay, we have a list, and based from that, we were able to somehow develop those groupings. So without you knowing it, your apps like TikTok and the likes, those are harvesting your behavioral data, and even your smartphones. Um, so these companies are able to take advantage of. Well, what I would just want to say is that they know more about you than you know about yourself. They know you better. What are your wants? What are your behavior? So yeah,
That's why there's so much legislation against TikTok because just the fact
not
that
only
it's
TikTok.
owned by China.
Yeah, that's one thing. It's owned by China, but other apps in the US they're also doing the same thing.
Yeah, but when
Look
it
at
comes to
Facebook.
when it comes to legislating, the idea that another country
Foreign,
with
yeah,
opposite ideals has that data on us is more threatening than Meta having that data.
exactly. So it's a question of national
Yeah,
uh,
exactly. It's national security
security,
in a way.
exactly, national security. With Meta, it's a bit relaxed relatively as compared to TikTok. Um, and you can gauge the characteristics of a country by the media they are consuming. So if you feed them so many trash contents, um, there's a significant negative effect. So be careful especially with your kids or uh, the young ones, your niece and the likes. Be careful on what they use online. Mm. These companies can attack the subconscious. They know more about us. They have this big behavioral data. So anyway, going back here, where are we? Yeah, with the certified random sampling, we just defined here um, the strata, and then on this part, after defining, okay, how many will be from the female, how many will be coming from the males. Now we will be doing it, okay? This is just one way, but you can do it in a different way. So basically here, this is a for loop, right? So for iterator in group, what would form the stratum data would be, okay, gender equal to the stratum. The stratum sample would be, okay, the number of stratum sample that we defined earlier, and that would form your stratified samples. Okay. Let me go back to my collab because I feel that it's not that clear. So let's dissect it line by line. Let's put it at the bottom. Okay. So now the certified sample. Okay. That is just the so this is just no. Something's not right here. So this is already mhm, right. This part right here. This is supposedly the complete case. How many do we have here? Dot info. Oops, sorry. Why did I put it on the? This is not supposed to be here immediately because this is already the 20 sample sizes that we have, and why do I have that in there? Let's see. Stratum give equals to gender should not be in here. PD.data frame. Stratum data. Stratified sample. Okay. Okay, let's focus on this part. Okay. So this is a for loop. Okay, this is a for loop that we discussed before. The for loop. So basically, we will be iterating. Okay, we will be iterating through this data frame. So this part right here, we are creating an object. We are creating here a data set which is composed of okay of um, based on the gender. Okay, so the stratum that we have defined earlier, where is that? The stratum that we have defined earlier would be this this groups, male and female. Okay, so that would be the grouping that we will have. That would be the stratification. Okay, groupings. And then here on the next part, what forms the stratum sample would be, okay, this part right here, this is just simple random sampling to each strata, to each stratum. Okay, so notice we are applying the dot sample. Why are we able to do that? Because this stratum data is actually a pandas data frame, right? If you look at the stratum data, this is of a pandas data frame, right? So we know the stratum data info, see its structure. Why am I committing that error every now and then? Okay, so we have 45 entries here. And I believe if you look at stratum data, the value counts, gender. Yeah, I need that one. Gender dot value counts. Okay. Okay, all of these are male, right? All of these are male. And then stratum sample, PD concat. This is just pasting together the stratified sample that we had earlier. Where is it? Stratified sample gender. That value of counts. I believe this is for the both the male and the female. Mm-hmm. And strata. See the so the first should be I'm missing the female group. Where is it? This is for the males. This should be the stratified sample. This is what we had earlier, right? Stratum sample. This is all male. So that is composing the 11. 1, 2, 3. Let me see. Length. 9. So that is correct. So this is the 9 that we have for the male. And then supposedly this should be for the females. Stratified sample should be the 20. Am I missing something here? Stratified. Age, this are male, 91, 63, 65. Stratum sample. Stratified sample. '93. So this is correct. This part right here. Where's the female? Stratum. EF gender, the groupings. There's something wrong with this because it seems that with this, it first completed the group for the female. Let me think. A minute. What am I missing here? For stratum in stratum data, DFDF gender, this is just accessing the gender variable equal to stratum. So the stratum here is the groupings that we've defined. So it could be the male or the female. So I believe this is the female first. And then for the sample, this is of leg 9, which is for the males. So we did a random sample given the sample size. Okay. So we got 9 from the males. So that is this. Sample. This is for the males. So after that, what remains would be 11, right? 11 that would be coming from the females, and that's where I'm missing that part. Start int. This is just allocation. I believe that should be the stratified sample right here. But this is already the complete case. Yeah, this is already the complete case. Let's make this part comment for now. And yeah, I think I'm missing something on this last part. Okay, missing something. Missing for the males, for the females right here. Well, let me go back to here. I think I missed some part right here for the female. So what this for loop does is it would first complete for one stratum. For example, that first stratum would be males. So it would complete first all of when it is equal to male. So as long as it encounters a male, it would form part of the resulting sample. So there would be 9 because we have defined it this way here. And then after that, what I'm thinking, but I need to verify it first, is after it completes the 9 for the male, it repeats that for loop for when the case is for female. But I may want to expound this line so that it will show us both the case for the males, like this one we're seeing here, the strata or the strato for the males, and I want to see the one for the females, not the complete case. Because what we have is already a concatenated version here. What I can do, I think, is to let's see. I can remove the concatenation here and just make it as a list. Let's see if this would work. Stratified sample. So now this is the group for the female. This is the group for the male. Sample 1. Okay. Male. And stratified sample. Stratified sample F. And then ed dot data frame stratified sample, and then here ed dot data frame stratified sample, stratum sample. And then I don't want to display it like that. I would be printing stratified sample M and print and print. It doesn't show again after I do a backspace. Sample F. I think this should work. Huh. Oh, I just don't want that. Only shows for male. Yeah, I think This only works in a combined version like this. This would be stratum sample, stratified sample, and then stratum sample. I think this is the easiest version to visualize it. To see the group for females and the group for males. I convert it into a data frame this way. My data frame stratified. Yeah, that's what I want. Huh. Empty data frame. Yeah, anyway, I don't want to waste so much time here. What I just want to show to you is this thing, the grouping between the male and the female. And I think this accomplishes that. I just want to present it in a much better way. But anyway, this would work. May need to need more time to convert it in a better way. But this is what I want to show to you. This is the grouping for the female and the grouping for the male. And if you count the number of females here, that would be 11, which is basically the one that we had earlier. Because for the 20, we base the size that would go from each strata depending on how they appeared in the original data set. So more females are in the original data set in the complete case. So there are 55, and there are 45 for the males. That's why we have more females here. Okay, we have more females, 11 females, and we have less males. So this is not the only way to do this. So basically, once you establish this groupings, this strata, okay, for each of the males or each of the gender, then you can just apply a sample into it and just concatenate it together afterwards. So what I was saying is, from this original DF that you have, what you can do after identifying the count that would form the samples, okay, based from the identified sample size. So what would be the first step into that is determine the sample size, okay, say 20 from our example. And then step number 2 is to identify the sizes for each of the for each of the um for each of the stratum. So if you have 100 and 55 is in stratum 1 and 45 is in stratum 2, that will be um 50 55 55% would be 55% of 20 would be your sample size for stratum 1. Okay. And then 45 would be for, how do you bring that back? 0.45 for stratum 2. Now, if you do the computation, oh, I don't want it like that. I only want this part to be comment. Okay. You would get print. You would get exactly the same as what you got earlier. This would be 11 and 9, right? And after which, you can get that number using simple random sampling. But first, you have to separate them into two DFs. So this is basically what we want to do: a DF for male and a DF for female, and then apply the sample, the SRS. Then apply the SRS within each DF. This is basically what we did earlier, but on a different I should say in a different way. Where's the SRS that we did earlier? This one. This one is what you want in this DFs. Okay. So you will be sampling, say sample M would be DF sample 20. So, and then after that, combine them together. Final sample would be DF dot concat, or PD rather, PD dot concat. Yeah, this two. So doing this process would actually give you the same thing. Concat. So you would still get a proper stratified sample with this. Okay, one with why oh, there we go. One with 9 males. I think we have much larger here. Is it 9? Gender. I forgot to specify here. It should be 9 and it should be 11, not 20. Okay. Sample. There we go. So this is the final thing on a stratified sampling done in a different way, but basically you're following the same principle. Okay. So again, you will not be doing this in Python. I'm just showing it to you for just for the purpose of visualization, seeing what's happening step by step. But this is how you would typically do this when you have defined what you want to answer your hypothesis. Okay. Then afterwards you'll be doing the data collection and identifying what specific method you'll be doing. But there probably in the future you'll be doing this in Python for the purpose of just answering a technical interview or something, just to just to show them that, oh, okay, I know how to do certified sampling in Python, or at least show you the idea, right, of a stratified sampler, or even a simple random sampling in Python. Yeah, I think I've burned so much time in here. I'm just missing, I think, a step I just want to isolate this too in a similar manner such as this. This is what I want to show you earlier. So anyway, moving back to our slides, we now proceed with cluster sampling. So the cluster sampling, oftentimes you would confuse stratified sampling with cluster sampling because both both with both you need to define groupings. But with cluster sampling, you would typically apply this when your population is distributed in a wide geographical area. So that's the main difference between a cluster sampling and a stratified sampling. Okay, and actually that's the major distinction between the two because the process also is almost the same. Um, so the idea with cluster sampling is you would be needing to define the clusters, not only the clusters, but the number of clusters that you need to do the sampling with. Okay, so let's have an example right here. Um, Another example in Python. So here we will be defining 5 clusters. Okay, so we have again a data frame, and we are just creating here random ages, random heights of size 100, and that would form our data frame, our complete case. And there would be clusters here. I just renamed this arbitrarily cluster 1, cluster 2, cluster 3, cluster 4, and cluster 5. And again, we're assuming here that they are spread over a wide geographical area, and those clusterings are the clusterings that you would observe. It's best to visualize it when you're in a plane and you're looking downwards, seeing the communities. There's a somewhat natural clustering, right? So when we run this and look at the resulting data frame, let's move back to Colab. If we run this part, this is the thing that we want, just to show to you how this data looks like. So there would be another variable clusters, right? So this person one with age of 56 and height of 194 centimeter, very tall, is belonging to cluster 4, right? And if you want to see the number of clusters in there, you can just hit it with a value count. So let's see the DF here, and we want to see the clusters in the frequency distributions for each of the clusters. So as you can see, it's almost of the same size. There's no much distinction between the clusters. So it's not always the case. In reality, you would observe that one cluster is bigger than the other, right? One cluster is bigger than the other. That's the typical setup. So this is just ideal because we use random choice, and this random choice assign equal probabilities for each of these clusters. That's why you have an almost uniform distribution of values in it. Okay, so that's how it looks like. Okay, and then going back to the implementation right here, where was it? At the bottom. So we'll be defining the number of clusters. This defining of the number of clusters, it's not arbitrary. It relies on your sample size. And let me show to you from the book that I was trying to finish. Intro to. I think I've showed you that before, but let me look for it again. Back 2020, and I could not find time to actually finish it. uh, I have there a detailed discussion of cluster sampling. Yeah, where's the cluster sampling? Yeah, there we go. So basically here, um, assuming that you have identified your sample size, you might be thinking at this point, Jeff, how do we compute for the sample size? It's a discussion that would require us one complete session because that sufficiency aspect of your sample size must be carefully discussed, must be methodologically identified. So you cannot just say arbitrarily that, okay, in this study, I'll be using 100 samples. Okay. If you want to achieve um, good representativeness, then you must achieve sufficiency. Okay. So there are multiple ways to do that. It could be method based. Okay. So there are different methods. There are different statistical methods that require different sample sizes. Okay, with regards to other considerations such as the number of parameters. Like for the case of regression, there's a rule of thumb there that for every predictors that you have, you must have at least 15 observations. So if you have one predictor, one X variable, you need to have at least 15 observations. If you have two, you have to have at least 30 and so on. But you can objectively identify that through power analysis. So there's a software, but you can also code that through Python or R that would allow you to analyze the power of your statistical test given a specific sample size, or do it on reverse, set a specific power that you want to maintain in your test, and what is the needed sample size in order to achieve that specific power of your test. Power in this sense, uh, this the ability. Okay, when we speak of power in statistical analysis in data analytics, we're not only referring to um, the power that we mentioned about level of measurement, right? We already defined um, statistical power in that sense related to the measurement of variable. There is another type of power in statistics and data analytics that is referring to the ability of your test to detect the existence of an effect. Think of it this way. Say the power of a person to easily see something that's hidden in an image, like what you would find in a Nestle Cocoa Crunch box. At the back of it, you will find like a game that you need to identify, like where is Cocoa or something like that in the back of a packaging of Cocoa Crunch. The ability of a person to easily identify where Cocoa is the power in a statistical test. Okay, the higher the ability to identify Cocoa or spot Cocoa easily means that person has a higher statistical power. Okay, because Cocoa could hide. I'm thinking if that's the best example for this. Maybe just using just using the internet would be beneficial for you. I don't want to I don't want to confuse this example that I'm not sure if you can follow. So here, statistical power analysis is a method for finding the probability of detecting an effect Okay, maybe the area of where Coco is the smaller the area, the more accurate. In a sense, yes. Think of it this way, Jeff. If the effect that you're looking for could be represented in terms of a relationship between your variables, if that effect is large, then you need less sample. You need less evidence because it is evident. I remember one good example. If you want to detect if significant difference exists between the heights of Southeast Asians versus the heights of Europeans, you need less sample size. Why? The difference is very evident, right? Even with just 10 respondents, you can easily see that Europeans are taller. However, if we visualize it this way, that you want to detect if significant difference exists between the heights of Malaysians and Filipinos, that would be a difficult thing to do because the effect is very small. That you need more evidence in the form of sample size to detect whether that difference exists. Does that make sense to you guys? The effect size, okay, if that is large, you need less sample size, even less power to detect it, right? And power and sample size are related with each other. But if the effect is small, okay, if it's very small, you need more sample size, you need more evidence to detect it. Okay, like if Coco is on Earth, it's less accurate than saying Coco is in LA if Coco was in fact somewhere in LA. Yes, Coco is difficult to find if you're considering the entirety of Earth. Coco could be in Hawaii, he could be in Croatia, chilling. So if you have that kind of setup, then you are saying that effect is small. There's so many places in which Coco could be. However, if we narrow it down, okay, Coco, find Coco in LA. It's the effect in this case would be much larger, right? Because you have less area to search Coco. Okay, so if Coco is in Hawaii and you start looking at LA, then you may need to expand your range. Yes, that's correct. That's the idea behind statistical power. The thing that you're looking at the screen right now. Okay, that's what we mean by the effect. Okay, that's what we mean by a power. The probability of detecting, okay, is the power of your test. There are tests that are higher in terms of power as compared to the other. For example, we mentioned a while ago parametric and non-parametric tests, right? Pearson and Spearman correlation. Both are correlational tests. But in terms of power, parametric tests have more power. They generally have higher power as compared to non-parametrics. Okay? So is it a game of expanding and shrinking? Exactly. Expanding sample size, there are so many benefits, but there are also disadvantages, costs, resources. But it increases your ability to detect the effect. In short, it increases your power. Okay, but you can only increase power as such. We will be discussing that, but you can only increase it with after you hit a certain point, there will be a significant increase whether you add more samples to it. So we are looking for the Goldilocks zone in which we will hit the maximum, not maximum, but the optimal power of our test. So less accurate, but you can find what you exactly. So the Goldilocks zone, the sufficient size in which we'll be investing less of our resources, but still maintain the power.
Hey, Jeff, is the same thing as when people, because I remember before vaguely when we did something, it was like sometimes we had to use log of something.
Sorry, the log or logarithmic?
Yeah, I remember before when we used to do something I forgot if it was a regression or something. Sometimes when we couldn't find
like when we couldn't, something failed or something like that, we had to take log of both sides and
Yeah, that's called variable transformations, and actually it's for a different thing. That's for parameter estimates because um, there are so many cool things when you do log transformation. Like for example, if your if your data has a skewed to the right distribution, let me show you this. It's like a magic, Jeff and the group. The transformation actually shifts the distribution of your um, data. Create me a data frame that is skewed to the right and apply log transformation for it. Use matplotlib to visualize before and after. Okay. I want to show you this so that you can have a visual of what I'm saying with that transformation thing. Okay. But it's for a different thing. Okay, it's for a different purpose. There we go. So as you can see in here, this is the original data set. So think of it as salary. Think of it as maybe waiting time. No, probably waiting time is not skewed to the right, but salary is. Salary is skewed to the right distribution, right? Very few are on the 1% of those earning more than 300,000 and so on. Now, I'll tell you that they are basically the same variable, but you just apply the transformation called logarithmic transformation. So there's a magic, like not really a magic, but when you apply transformations, yes, logarithmic transformation, it shifts the distribution of your variable. So from being skewed, you see that it is quite normal now. But there are benefits as well as repercussions for that. One benefit is you can apply parametric methods with this now. One disadvantage is interpretation. If here you can interpret it in the same unit as with the salary, if it's US dollars and so on. Now, if you apply logarithmic transformation, that would be logarithmic of US dollars, which is not very intuitive to most people. And this somehow bias your parameter estimate. So you should do that with utmost care. Okay. So that is well way ahead of our discussion, but just to answer Jeff's question. So going back, not a question, yeah, Jeff's question. So going back here, just to make sure that we're on the same page, when I speak of statistical power, it is the ability of your method to detect the existence of an effect if it really exists. Okay, if you forget it, just remember my example about comparing the heights of Europeans and Southeast Asians versus within Southeast Asians, like heights of Filipinos or Malaysians or Singaporeans. It's significantly more difficult to detect the difference. Okay, so more sample size, higher power. Less sample size, less power. Okay, larger effect, needing less sample size. Smaller effect, needing more sample size. So that's the balance. So you need to strike that's the trade-off. You need to strike the balance. Okay, and how do you do that? It is through power analysis. So the reason why we discuss that is because um, we are discussing this. Okay, we are discussing data collection and sample size. So we mentioned sample size here. how we compute them. Okay, we'll reserve a separate section for that. But going back to the cluster sampling, after you have identified your sample size, you will use that later on to define the number of clusters that you'll need. Okay, so here we'll estimate the number of or average number of students per cluster if the exact count is not available. But in our case, it's available. Okay, so here we have an assumption that there are 500 students, so we divide it by the number of sections to get 100. So that is our estimate of the number of average number of students per cluster. Okay. Now identify the number of clusters that we need to do the sampling with by dividing the sample size by the average number of students per section. Okay. So here your defined sample size 150 will now be divided by the number of or estimated number of or estimated average of students per cluster. We don't need to do that in our case because in our case, we have an identified number of inputs in each of the cluster. So we can just get an average of that, okay, in order to form the number of clusters in which we will be doing our sampling with. So going back here, we will not be again doing this process because in our case, it's already identified. You have cluster 1 that contains this number of individuals. Where was that? I lost my collab. Where was it? Here. So we have those clusters already set up, right? So here we have 24, 21, 20, 18, and 17. So to make things simpler, we'll just assign, okay, we need 2 clusters to sample. Okay, here we defined it. In this part, we defined it. But if you want to be more methodological, what you want to do is to compute for the average, right? Average of this, it's not very difficult. You can just create a list out of it. Even you can directly compute for it even without forming a list. 24, even a tuple, actually, it would work. You can apply the dot mean here. Oh, really? Let's try with list. Okay. If you don't want that, then what I'll do is just get the sum, or I can just create a df here, num, a, okay, and then I have those values, and then convert that into num df to frame num, and then I'm now sure that I would be able to get a mean out of that, but this is like an overkill. You don't have to go over through that. You can just immediately compute for it. This should be a list. The values should be a list inside the dictionary. There you go. So the mean is 20, right? So going back to our discussion a while ago, the sample size would be divided by the average number of units that you have. So suppose that here, what is our defined sample size? So we base it here on the size. So it's actually a proportional allocation in this, but it's not necessarily like that. What you can do is your computed sample size will be divided by this. So if your computed sample size is say 200, say sample size is equal to 200, then you just divide 200 by 20, and you'll have which is very which is, a very large value, I guess. So that would be 10 clusters. Very large value. Okay. So here in this example, instead of doing that in this implementation, this is a proportional allocation example in which this part right here actually identifies the sizes, right? So this part, if we would separate it here, that would actually give us got to print it. Print clusters. Clusters. Yeah, it would just give us this 1, 2, 3, 4, 5, our first 5 clusters, and then we'll be allocating. Um, will be we would be choosing, okay, given equal probabilities, out of that 5 we'll be choosing 2. Okay, so that is our selected clusters now. So let's see that. Let's see the clusters that we were able to get. So 4 and 5. If you repeat this process, if you rerun this, then there's a possibility, if you don't have a random seed right here, you'll get a different cluster. But since we have a random seed here, we are assured that we will get the same instance in the selection. We'll still get 4 and 5. But if we remove this part right here, we don't set a random seed, you would be getting a different cluster. Maybe 1, 3. Yeah, 1, 3. Okay. So the good thing with this is we're not relying on our own with the selection of our clusters. Okay, because in sampling, what we try to eliminate is the bias. So if we ourselves decide on which cluster to do the sampling, then well, subconsciously we might inject some bias during the process. So we're removing that aspect. We're removing that potential source of bias. That's why we randomize the choice of cluster selection. Think of it this way: when you're doing an experiment, you're also eliminating that potential source of bias in the selection of your experimental units, because in the choice of the experimental units, um, in most cases, those are the potential sources of the term or the detected effect. For example, you are trying to evaluate the efficacy of your diet program, and you don't do randomized selection. Okay, you chose based on your own evaluation, and you thought, okay, you decided to choose this already active individuals, fit individuals, and because of that, after your experimental duration, you found out that all of them are fit. Okay, and you concluded that your diet program is effective. So what I just want to just communicate here is that we are trying to randomize the selection process to eliminate as much as possible the potential bias that we can inject if we do the process alone ourselves. Okay? So that's what we are eliminating here. So let me put it into writing here. We eliminate the potential bias that we can inject. That bias could be injected subconsciously. Okay, even you do not intend um, to associate the bias. There's a real chance that you would subconsciously do that. So we're removing it through a randomized selection that we can potentially inject, that we can inject in the selection through this. Okay, so this is a very important step. Again, sometimes in studies, the existence of the effect is not really associated to the effect itself, but because of the selection. The efficacy of the diet program is because of the selection, not really because of the diet program itself. So it's a false positive error. You thought that that there exists an effect. In reality, there is none. Okay, that's one grave error that you can commit in statistics. Like for example, you're developing a drug for COVID-19, maybe during the 2021, during the onslaught of COVID-19, and you did not randomize your selection. You subconsciously injected the bias in the selection of your participants. And in your study, you found out that this particular um, vaccine works in reducing the fatality of COVID cases. And that's an effect. Okay, that's an effect. That's significant. Only to find out that the existence of that effect is only due to the selection error, the sampling error is typically what they call it, sampling due to sampling error. So in that case, you're committing a false positive error or an alpha error, type 2 error in statistics. You concluded an effect when in reality it doesn't exist, and it's a very grave error. So you with that vaccine, you sent it to hospitals or injecting to the frontliners, and they became complacent because they thought that it is indeed effective, when in fact the effect is just due to sampling error and it's not really existing. So be very careful with this, and always take into consideration randomized selection to avoid sampling bias. Okay, and then here we just applied here a multiple OR. Okay, the selected cluster. So we will be selecting data, sample data from the selected clusters. So in the selected clusters, particularly 1 and 3. So this cluster sample would now be our final, and it would consist only um, from clusters 1 and 3, right? Those that we have identified. So you might be thinking, Jeff, why don't is it a representative if we only select sample? Could we achieve representativeness with this? Or is it better to just do proportional allocation and have all of the clusters um, have representative or samples? Anyone? Am I still making sense with the cluster sampling, guys? Why we only have cluster 1 and 3? This is second to the last of the sampling methods. Again, it's not necessary to deal with it in Python, but I just felt that it is more proper to have a visual of it. Anyone? What do you think? Is it better to get only 1, 3 from 1, 3 and not from 1, 2, 3, 4, 5? Not distribute them from 1, 2, 3, 4, 5? Any guesses? So the answer here lies in your sample size. If your sample size is sufficiently large enough um, to accommodate more clusters, then so be it. You'll have more clusters in it. But it's nice. It's not proper to distribute a very small sample size into many clusters. Like for example, you have 5 clusters, and you're only getting 40 sample size. You'll be distributing it into those 5 clusters and get only 8 from each, right? The ideal setup here is you have a large sample size that you'll be distributing to um, have more opportunity to allocate that into more clusters. Okay. So with this computation that we had manually, it is all based in the sample size that you have. Larger sample size, you have more clusters to to get your sample from. And of course, the process in which you'll be getting that from each of the clusters through random sampling again. So where is that in here? You can find it in the sample. Where is the selection here? PF clusters, and so this part right here is actually doing the selection. Okay, it's doing the SRS in here. So SRS, not as a filter. The SRS is here. So, as compared to certified sampling, you would less likely use cluster sampling. Okay, this is typically done when your population is just spread over a wide geographical area. Most of the time, it would be stratified random sampling. Okay, and to finish our discussion with data collection, we are now on the systematic sampling. For me, systematic sampling is the easiest to process, easiest to understand, because in systematic sampling, you will get the kth member of the population. So suppose that your k is equal to 3. So we start with the first, then you will skip every third. Okay, you will get every third, not skip. So you get the first, the third, the sixth, and so on. So that's systematic random sampling. So this is cluster sampling, just a visualization of systematic sampling. So what you can see at the top is the simple random sampling. Okay, there's no obvious pattern. Right? These are the samples from 0 to 100 or 1 to 100. Then you have a stratified random sample. So there's a bit of structure in here. So you can think of the stratification as the ranges, like 1 to 10, um, or 1 to 19, 20 to 30, 40 to 50 and 40 to 49, 50 to, and so on. So those are the stratifications. And then the clustering, as you can see, it's um, very structured. Is very structured as compared to stratified and simple random. And lastly, you would see the systematic sampling. Systematic sampling, it's spread evenly, okay, in your population. If you would ask me um, if systematic sampling is better than simple random sampling, there are cases in which it is. Like one of the project that we did when we surveyed those people that are boarding ships. So how did we do the systematic sampling? As people on board the ship, we just set up a value of k so that we can do the systematic sampling. So for every k that will onboard the ship, that would form part of our sample, or we will be giving them, we gave them survey questionnaire. So in that setup, systematic sampling is easier to execute as compared to systematic to simple random sampling. With simple random sampling, you would want them to all of them to have on board the ship first before you do the sampling procedure, which I think is more complicated than doing systematic sampling. Um, Having the key that would onboard as part of your uh, set of samples. Okay, so those are the um, different probability sampling techniques and how to choose a particular technique. There's so many considerations, but I've identified uh, four, I should say, significant, okay, consideration. First, the size of the population. If the size of the population is huge, then it's almost impossible for you to do SRS or simple random sampling. It's almost impossible for you. So cluster sampling in this case would be better. You could cluster by, say, state. Okay. Accuracy requirement, high precision. So if you want to have high precision, then stratified sampling, because in those strata, okay, there would be less variation, less variability. So those groups tend to be homogeneous in terms of characteristics. And complete list of population, if you have that, then it's best to have equal chances, to give equal chances for each of the elements. Then you would be using SRS. Study type, if longitudinal studies, then it would be systematic sampling. And again, depending on the like what we did in the past with the survey on those who use ships in transportation. So those are some considerations, and this must be clearly identified before you do any um, any sampling. Okay, so that's what we have for this data collection lecture. I know that I think there are parts in this lecture that are probably vague, but how should we supplement it? We would be supplementing it by more cases, probably during lab, John, if you're already there. Probably during lab, what you can do is to have further examples, whether in Python or just conceptually discuss this different sampling process and weaknesses and strengths of each. I think that would solidify the foundation. Okay, so for the next session, what we will do is um, discuss visualization. How do we visualize our data based on certain levels? And I think we haven't done that in Python session, so this would be the perfect time to do that. How to do pie charts in Python, how to do um, bar charts, and interactive charts. So that could be our Wednesday and probably until Saturday session. Okay, everyone? So thank you very much for attending the class. And yeah, I hope you learned something new with this discussion. And if you have questions, please let John know. And yeah, I kind of stepped back with the idea of giving you reading assignment because I think it defeats the purpose of having labs and lecture sessions. So I just leave it with John during the lab sessions for any clarifications and for further discussion. If uh, if something is really confusing. So thank you very much, everyone. Bye bye. John, sorry, I used your time in
Thanks, Jeff.
lab. Yep. Thanks, Jeff. Pasiba, Grace.
Bye. Thank you.
Bye bye.
Hello, everyone. Can you hear me?
Yeah, I'm here.
How was the session?
Oh.
Heavy again, I guess.
Long, informative.
So, but tomorrow, what I plan is let's have an actual data set and let's practice the chi-square as well as the t-tests. And let's say some of the assumptions of t-test were violated. What are the things that we can do alternatively?
Awesome. That was my concern, was just some practice.
Okay. And tomorrow we will practice that. So wait, I guess I can open my camera because we will just have a couple of minutes left. Later, a while ago, I'm off cam because we don't have an internet right now. We don't have a Wi-Fi connection. I'm just having what is it, hotspot connected on my
Hotspot. Wow, your hotspot is pretty
yes,
good.
on smartphone. This this I guess I am also
My
surprised.
hotspot is really bad. I can't do this with my
Like sometimes it is not working very well, but I'm thankful that it is working well right now. So I can also join the class. So our agenda for this week. Wait, I created a calendar for that. Let me find it first. I kind of arrange all of the things that we will perform for the entire week because it is stressful if I will just think of the schedule. So I actually wrote it down. So today, we just plan to have some recapitulations and some announcements on schedule, but I think you are already exhausted on the heavy amount of information about statistics. But tomorrow, we will have an actual practice about the t-test as well as the chi-square tests. If we still have time, we will try also to cover the correlation and regression, the one that you have performed um, earlier, the one that was shown earlier. If we still have time. On Wednesday, another sets of discussions. I'm not yet sure of the things that we will do on Wednesday, but Thursday, you will have an activity, hands-on activity. T-test and chi-square, like somehow an exam but not graded because it came from me. To for you to let's say you will be the one who will perform the steps and processes like checking of the assumptions, writing the problem, writing the null and alternative hypothesis, setting the critical region when to reject the null hypothesis. So you will be the one who will perform that. So on Thursday, it will be a hands-on wherein um we're still on the meeting. So think of it like somehow you are having an exam, but it is not an actual exam. It is a time for you to perform the task. We're still on the meeting, so if you have any questions, you can type it on the chat box. You can unmute, and I will try to reply as soon as possible. But we're still on the meeting. On Saturday, discussion, and Saturday I also planned that that will be also the time that we will check if the things that you have performed on Thursday is correct. What are the things that you might improve? What are the things that are good? Like, what are the correct things that you have performed? So that will be our plan for the Saturday meeting. So yep, that are the entire week for us trying to perform actual statistics through Python and verifying if that is correct. Okay. Do you have a suggestion on that schedule?
That works for me, I think. I don't know.
So I will make the files easy to understand. Like, not easy to understand, but the instructions were clear in such a way that if you will read it, the confusions are minimized. Okay. So I guess today you have also covered the sampling techniques, but maybe on 10 minutes let us summarize the things that you have. Let us summarize the wait, let me check my hold on. I think I have that drawing wherein it summarizes everything about that concept. Okay. So let me share my screen. I will join this device also and there's a problem. I can't show my screen because it needs authorization to connect on the internet. So let me just summarize the things that is about the sampling. So as you know, there are two types of sampling. One is probabilistic. So I guess I will just share my screen and somehow visualize this through Excel. So there are two major types of sampling. One approach is probabilistic. One is non-probabilistic. Non-probabilistic. So why this thing is important? So this thing is important as soon as you you wrote the problem clearly. You would know what approach you need to use. Like, let's say you are interested on generalization. So you want to create inferences, generalize. If that is your goal, you need to have probabilistic approach. So this is when you want inference or generalization. But non-probabilistic approach, it is being performed when your when the participants that you are interested in are rare, so one of them are rare. What else? The information are critical. That's one round also. And commonly this is performed when you have a research that is qualitative. So somehow you are interviewing life coaches, experts from the field. So that is non-probabilistic approach because not all people are experts and not all people are under that particular group of people who are experts in that field or rare in that field. Let's say, for example, in the Philippines, since drugs are there are illegal drugs. In general, there are illegal drugs. There are some studies that is about illegal drugs, but you are thinking how do they found respondents on that? The approach that they applied is non-probabilistic. They can't just sample and just pick random person in the Philippines because the person that you might get is non-user of those illegal drugs. Under probabilistic approach, there are four major types like the simple random sampling. Simple random sampling. What's the idea of simple random sampling? All of the people on your population have equal chances of being selected. It is like a fishbowl method. Like on a fishbowl, there are pieces of paper wherein their names or IDs are all in there and you are picking randomly. So that is simple random sampling. We also have the stratified random sampling. Stratified, you have stratas. Let's say strata 1 to 4, let's say first year, second year, third year, and fourth year college students. On each strata, you are performing simple random sampling until you reach the minimum number of samples. So it is like a simple random sampling, but you are performing them on each strata of your population. The next one is the cluster random sampling, and this is being performed when the location is challenging. It is due to the um, geographical limitations that you will just consider all of those people on that area to represent the population. And what's the other one? Systematic random sampling. Systematic random sampling, this is also simple random sampling, but in the way that you have a list. You have a list of the population and you are computing an interval wherein, let's say, every fifth person in the list will be a part of your sample. So that's the systematic random sampling. But the idea is people selected under the simple random under the probabilistic approach, they have this chance of being selected. For the non-probabilistic approach, people don't have equal chances of being selected. So what are the types under this? So we have convenience sampling. So maybe one time that you go to a store, to a mall, there are people that are handling out they are handling this handouts that you need to fill in, like a rating for a specific product or maybe somehow in the form of free tastes, like before they launch their product they will offer free tasting and then they will ask you what's your rating for this product. So convenience because um, they will just offer the being part of the study to those people that are near them. So it is pretty convenient from the word itself, convenient sampling. One is snowball sampling. This one is common for sampling, especially those areas that have crimes. Let's say criminals, let's say illegal drug users. So you would get your goal is to find one illegal drug user and prompt him or her to lead you to other users. And that way you could get the samples that you need. But not everyone has the same probability of being selected. So snowball sampling. And what else? There are many things under the non-probabilistic approach. I forgot the others, but here, since we are focusing on the data analytics, we are more concerned on the probabilistic approach. And commonly, the thing that we will encounter is the simple random sampling. For those studies that includes surveys, the common one is the systematic random sampling, especially when the setting is the school, universities, because you can get lists of the participants that are actually attending those institutions. So to keep it simple, there are two types of sampling, probabilistic and non-probabilistic. And if the nature of your study or your analysis is to make generalization, the sampling that you should perform is probabilistic approach. Because the people that you would select under the probabilistic approach ideally are those people that represent your population. So whatever the characteristic of your population is also the characteristic of your sample in some degree of confidence. So something like that under the sampling. But I guess this sampling part, we will not perform this. If you are the analyst, this is not your role. Like, it is not your role to collect the data. It is a role of your another teammate. I'm not sure if I shared to you the data analysis structure wherein there are people that are designed to collect the data. There are people who are assigned to design the connections within the data, and then there you are, the analysts, wherein your main goal is to make sense out of the data. So these things, why are we talking about this? Before we analyze our data, we should be sure that the data that we have is probabilistic, so that whatever insight that we could get can be generalized. It can be applied in our it can be decided that that is the thing that is really happening, let's say on our customers, or on our products. So I guess that's pretty much it about the sampling. I'm sure that Sir Jeff provided you a lot of explanations on that. I just summarized it in the way that you somehow have an overlook of this thing. Okay, tomorrow, let's try to perform actual t-test, chi-square, and if we still have time, correlation and regression analysis, simple linear regression analysis.
All right. Thank you, John.
Okay, thank you, Grace.
Thanks, John.
Thank you,
Bye.
Jeff.
Hey, John, before turning off, I just have a question. Whom should I approach to fix my
Canvas.
canvas? Yeah,
Wait,
I sent a screenshot.
have you asked Jeff and Grace if they encountered the same problem?
I left the message in chat box, so I think they saw and they didn't respond.
Wait, let me check if you are still on the roster of the students. sometimes the canvas is acting weird. So what
It
I can
says that you don't
suggest
have any course to this page. I sent a screenshot.
is
to
I
your
saw
answer.
your screenshot and
Mhm.
you're still here. hasiba.sarfaraz@gmail.com.
Yeah.
What I can suggest is to check if you are using the account, the correct account that you have. You
Yeah,
can
it's
you
the
share
same
the
account.
screen? Can you share your screen so that
Oh, sure.
we can see what is happening on your end?
Can you
And
see it?
yes, yes. Wait, permission to off my camera because I think there's a warning already on my phone that I consume so much data this day.
Oh, no
Okay.
problem. Maybe I
Okay.
can do it
Thank you for that.
tomorrow.
No, no, no. We can perform it now so that
Okay.
tomorrow you can focus on the activity. So
Okay.
can you
So
click
this
the
is my
account?
account.
Okay, account and then profile. Can you go to the profile? This is okay, wait. Can you click the account and then log out and then we'll try to log in again.
I don't remember my
Yes,
password.
log out. Oh, you don't remember it. Wait.
Yeah.
But I think you are using a different account. That's my guess because looking at the records, you're still here.
Yeah.
You're
If I
still at
log out,
the
but here, I have my password saved. Let's do it again. And this is,
wait, let me send you a message on the canvas and let's see if this will notify you.
sure.
Confirmation. Okay, I sent a message on the canvas. Did did you receive any notification?
No, let me refresh it. I think
So,
so.
oh wait.
Yeah.
Okay, open that, click that one, and then reply. Do you have an option to reply?
I don't think so.
Oh,
Maybe here. No, it's not working.
what happened in your canvas? Can you click the history under the
History.
inbox? Yes, under the inbox on the left part. Courses. And wait, can you click that course announcements?
Access
Oh, why,
denied.
wait. Hmm. Okay. What I can suggest now is to reach out Miss Sherry about this.
Sherry.
Yes. Have you talked
Uh,
to her previously or not yet?
no.
Okay.
How should I
So,
find her?
okay, I will talk to her and I will raise your concern. But can you can you send me some additional screenshots so
Sure,
that
yeah.
okay, like that one access
Yeah,
denied bot, that access denied thing.
yeah. I will do that.
And also the thing that you would see when you open the canvas. Can you close your canvas link
Yeah.
and then open it again? Or just
Like
refresh?
log out?
Okay, go to the account. No. Oh, okay. Can you can
I sent this screenshot as already.
Okay. Okay. Canvas, they don't have any courses right now. And click also the history, the screenshot of the histories, so that because there you would see that previously you still have access on the files.
Okay.
When's the last time that you accessed the files? When is the
I
last
think
time?
it was Friday. Friday,
Okay.
I think, or Saturday.
Friday.
I sent the my homework.
Okay.
I submitted.
I guess that's the last time that you have access it. Okay, for now, let's stick into this. Don't worry, your records are still on my end.
Okay.
So your records are still here.
Okay.
What we need to do is for you to join again the class. But
Okay.
wait, let me figure out that, let's say 2 to 3 minutes. Let's see if I can do something to invite you again on this class.
Yeah.
People. Under the people, you're still here. Okay. I resent an invitation.
Where can I see that? Where's it? My Gmail?
Maybe on the Gmail, hasiba.sarfaraz at
Yeah, it's the
gmail.com.
same.
Maybe on the Gmail.
Yeah, I just opened through the Gmail. This one.
Wait, can you go back again? It should be an IDE class. At the inbox, can you click the inbox again? Inbox. I think that one.
Yeah.
You're not receiving the notification that you should receive.
Yeah.
I wonder
So
what's the
I have
problem.
Yasmin's contact. Can I contact her, or is there someone special to take care of this stuff?
Typically, it's Miss Sherry that you should
Okay.
contact. Sherry, wait, Sherry May Perez. She's on the admin, so she handles most of the.
Can you share the her contact with me in the chat box?
I put her name on the chat box. Sherry May Perez.
Like an email address or something.
Wait, you can message her through MS Teams.
Okay, sure. Thank you so much,
Wait,
John.
wait. You can try messaging her now through the
Okay.
MS Teams.
Okay, sure. I will do that.
Okay. So
Yeah.
I think it will automatically appear Sherry May Perez at the if you search her.
Okay.
Okay.
Sure. Yeah.
Okay.
Thank you so
So
much. Have a good one.
thank you.
If I will,
See you tomorrow.
I will text you if I couldn't do that.
Okay.
Yeah.
That's great.
Mhm.
Thank you,
Bye.
Hasiba.
Yeah. Have a good one. Bye.
Thank you. You too.